こんにちは。今日のスピーキングを始めます。Electron microscopes. The electron microscope is so named because it directs a beam of electrons rather than light through a specimen. The beam of electrons is created in a hot tungsten filament in an electron gun. This beam then travels through the length of the microscope cylinder, which houses the lenses, the specimen chamber, and the image recording system. Two types of the electron lenses are used, electrostatic and electromagnetic. They create electric and electromagnetic field to both concentrate and move the beam. The electron microscope requires that the electron beam be in a vacuum, because electrons cannot travel far in air at atmospheric pressure. The crown and specimen chamber of the electron microscope are evacuated by pumps. Living specimens cannot be examined with an electron microscope, since they will not survive in a vacuum. The magnification in magnetic electron microscopes is determined by the strength of the current passing through the electric and electromagnetic lens coils. The image is focused by changing the current through the objective lens coil. In the optical microscope, the image is determined by absorption of light by the specimen. In the electron microscope, the image results from a scattering of electrons by atoms of the specimen. Since an atom with a high atomic number scatters electrons more than does a light atom, it appears darker. As the beam passes through a specimen, each tiny variation in the structure of the specimen causes a variation in the electron stream. The image produced is then projected onto a fluorescent screen or recorded on film. The electron microscope, with its tremendous resolving power, can magnify specimens over 50,000 times. Offset printing. In the past few decades, offset printing, also called offset lithography, has replaced letterpress and intaglio methods almost entirely for commercial work. The name offset refers to the fact that the printing plates do not come into direct contact with the paper. Instead, the inked printing plates, which are attached to a cylinder, transfer or offset the image to a rubber blanket covering the cylinder. As the inked blanket cylinder rotates, it deposits the image onto the paper, which is fed from another set of rollers. The offset technique was made possible at the beginning of the 20th century. After the development of certain photographic processes and the rotary wave press, offset printing plates are usually made of steam, aluminum, or chrome copper alloy. Unlike letterpress or integral printing, offset does not depend on light or etched surfaces to transfer images. Instead, it relies on the fact that grease and water do not mix. As the plate cylinder rotates, the plate passes first under water-soaked damping rollers and then under inking rollers that carry a grease-based ink. The offset plate is chemically treated so that the area to which the ink is transferred retains the greasy ink and repels water. The rest of the plate retains water and repels ink. As the cylinder continues to rotate, the plate passes against a rubber blanket, which accepts ink from the plate and transfers it to the paper. Since there is no time to wear out, an offset plate can make a large number of impressions. Offset presses can be designed to print both sides of the paper at once or to reproduce images with one or more colors. Water, oil, and gas. Oil and gas are primary mixtures of compounds of carbon and hydrogen, known as hydrocarbons. They are formed as part of a natural cycle which begins with deposits of plant and animal remains and fine sediment, trapped over millions of years, often deep beneath the ocean. This organic matter is transformed by the combined effect of temperature and pressure into oil and natural gas. The formation of oil and gas deposits or reservoirs occurs when these hydrocarbons migrate upwards through the rock layers toward the surface. These hydrocarbons often escape to the surface, where they may form natural oil seeps or, in the case of gas, simply dissipate. Any hydrocarbons remaining on the surface are soon oxidized by bacteria. Sometimes oil and gas are trapped in deep underground structures, which prevent them reaching the surface. They may be trapped underneath curved layers of rock, called anticlines, or by faults in the rock. Faults occur when layers of rock split and move, such as in an earthquake or during normal seismic events. The term reservoir can be misleading, giving people the impression of large subterranean lakes full of oil. In fact, oil and gas are trapped within porous sedimentary rocks, such as sandstone or shale, and may occupy as little as 5% of the rock volume. Convergent boundaries. Because plates cover the globe, if they separate in one place, they must cover it somewhere else, and they do. Plates collide head-on along the convergent boundaries. A profusion of geological activities is associated with a plate collision. One plate sinks beneath the other, a process called subduction. Ocean lithosphere thus descends into the asthenosphere. This down buckling produces a long, narrow, deep sea trench, about 100 kilometers wide, where the ocean floor reaches its greatest depths, about 10 kilometers below sea level. The edge of the overriding plate is crumpled and uplifted to form a mountain chain, roughly parallel to the trench. The enormous forces of collision and subduction produce great earthquakes. Materials may be scraped off the descending slab and incorporated into the adjacent mountain. Imagine yourself as a geologist attempting to figure out the meaning of such tangled evidence. Furthermore, during subduction, parts of the descending plate may begin to melt. Magma formed where plates sink into the mantle floats upward and can reach the surface and erupt from volcanoes. Recall that divergent zones are sources of new lithosphere. Subduction zones at boundaries of convergence are sinks in which lithosphere is consumed by being returned to the mantle. Energy and resources. The Earth's crust consists of a relatively thin layer of rock lying above the mantle. A region of high temperatures and pressures geologists call the rate of increase the geothermal gradient and measure it in degree per unit of depth. The geothermal gradient varies from place to place, but it is usually higher in crust beneath the sea than in thicker continental crust. Engineers can exploit the heat wherever they can reach it. Geothermal energy schemes go back thousands of years. Reservoirs of hot water can lie close to the surface where local geological conditions allow. Such reservoirs occur in permeable rocks, most commonly in seismically active regions. These are often close to the boundaries of crustal plates, for example, in Iceland, New Zealand, and Italy. Converting the energy to electricity is also not a new idea. The first generator driven by geothermal steam began operating in Italy in 1904. Today, geothermal power plants around the world have a capacity of more than 2,000 megawatts. Together with geothermal projects that supply only warmth for space heating rather than electricity generation, this adds up to at least 10,000 megawatts of geothermal energy already in use. Engineers could extract more of this heat if they could find a way to drill economically through impermeable rocks to depths at which temperatures are high enough. In a development project run by Britain's Central Electricity Generating Board in Cornwall in southwest England, the geothermal gradient is normal, but decaying radioactive elements give the rocks extra heat. 終わり